4 by 4 by 14 beam, 4 by 4 by length is 14. We also made these plates, okay, so which are only about half an inch in thickness. Okay, are you getting me right now? So yeah, those are the beams. These are the plates. So these are about 1 foot length. Just to recall, 3 inch in width and about half inch thickness. So these are now solid. Hamid and Ketan demolded them 24 hours after we cast, and today is exactly 28 days after that specimen casting that we did. And the third kind of specimen was these cubes. Okay, so as with all other specimens, there is one surface which is very rough because it's the top one, but it's still quite smooth. But the other ones are perfectly smooth. So we will test the cubes along these two smooth sides. Okay, so you can see and examine if you want. I have more of these, so you can see. So you can also see the air flaws on the surface itself. So such flaws are there throughout the material, although lesser inside, but due to the pressure of the material from outside. But yeah, it does contain some flaws. Okay.
This is the yeah. Okay.
And this is the plate specimen. If you want to take a look at that. So you can see that. So here, our original plan with the plate was to pull it under direct tension. Okay, that was our original plan. So that's why we made these specimens under uniaxial tension. However, the gripping system is not perfected yet. So what it does, it creates a lot of stress concentrations here and here when we grip it. So in our experience of the last 4 specimens, all of them failed over here very prematurely. So we will just do bending test on these plates today, like the beam test. So we'll test everything in Flexure and then remove this setup and then just do the compression on the cubes. Okay.
So we fracture this?
Yeah, we'll fracture it in bending. Okay, not under direct tension. So, yep. So let's start with this plate. So we'll place it over here in the center. Now here again in the Flexure, when we are doing the Flexure test, the ideal load scenario is the 4-point bending test, which has 2 rollers on the top as well. Okay. So like it has 2 rollers at the bottom, it has 2 rollers at the top, exactly at third of a length, L by 3, L by 3, L by 3. So the idea for that is to create a constant bending moment. So you all know the bending moment of a beam, so it would go PL by 6 and then constant, and then it will go to 0 again. But again, due to the constraints of this setup, so this setup is actually for the longer beams. 6 by 6 by 18. So we can do 4-point bend test, but on a longer specimen, not on a. This is not meant for bending a plate. So we'll just do a 3-point bend test, not a 4-point bend test. Okay. So there is only 1 roller on the top. Okay. So now the bending moment will have a triangular diagram. The problem with this is you don't have a constant bending moment in that center. You don't have that. Okay. So you are setting yourself up for failure because you are applying the maximum moment at just one section. Okay. But even in spite of that, because the material is strain hardening, you will still have some multiple cracking and tensile ductility, which you don't ever have if the material is not strain hardening. Okay. So it is only because of the strain hardening ability of the material that you will still be able to have multiple cracks, because the bending moment will go to its elastic capacity and still keep increasing after that point. Okay. So let's try this out. So the plates are ready. Chris, you're good to go?
Yep.
Okay. So let's switch this on here. I will stand here. Are you able to get that, or do you want to move over here? A little bit. Be careful, be careful.
That's good.
So this is a simple hydraulic machine. Well, it's a electro-hydraulic, servo-hydraulic. So this valve actually controls the rate at which it will go up. Again, ideally we would like to run this on that machine, which is the MTS. So there we can, the loading is displacement control rather than force control. So here it applies a particular stress rate, not force rate, not displacement rate. Here. So it has already started to load the machine, load the plate. But it will go to a load level and then just be steady at that point, because then after that it will undergo inelastic deformation, start yielding. So if you hear closely, you can actually hear the fibers breaking or pulling out. Yeah, stand over there. Go ahead. You will see like. Can you hear that? Yeah. So that's those fibers are pulling out of those cracks. Some of them are breaking. Yeah. So see now the load is kind of stabilized. There is very small curvature in the specimen. Faster. So 60 was at elastic and now it's taking more load, so it has reached to 70. So another drawback of this testing this small plate over here is that the least count of this machine is 10 pounds. So you cannot see any load between that. Because this is not built for measuring this. It is supposed to go up to thousands of pounds. So maximum capacity is 300,000 pounds. So you cannot have a least count of less than 10 pounds for such a high capacity machine. Yeah, now you can come here and look from the side. So you can see a slight curvature developing in the plate. See that? So typically it's concrete, it's not expected to bend, but this concrete does. So are you able to see some kind of bending on the camera?
On the camera?
Yeah.
More or less.
Yeah. Maybe can we zoom it in a little bit? I just want to see the blade really.
Okay, so
Whatever we can. Yeah, yeah, that's okay. Alright. Yeah, so it's bending quite a bit now. Now it's very obvious. If you want to take a closer look at it, you can.
Yeah, I can see.
You can see the bending, yeah, okay. So we'll pull the plate out later and see the back part of it. And there you can see all the multiple cracking, like a regular reinforced concrete beam. but there is no conventional reinforcement, of course. We all made it in the lab, right? Okay, load is going down, so that means it might be close to being broken. So now I am retracting it, okay? So retracting actually, since it was most of it was inelastic deformation, so it will still have that bend, but some of it was still elastic deformation. So that curvature that has been created will go back up a little bit, okay, as we remove the load. Okay. Now I'm pulling this out, and for the camera, I will show point. No, that's fine. Let him where it might go. Can you see these cracks?
No, let me zoom out.
Yeah, zoom out. No, why are you changing that?
Because
Because
right now
they're the
it's,
same. It's not in the same place.
Okay.
if you bring it a little
Yeah.
that side. Yeah, perfect.
Okay. So you can see all these multiple cracks over here at the bottom of the plate. Okay. So if we did the 4-point bending test, so the rollers would have been somewhere over here. So you would have seen such saturated cracking all the way from here to here. Okay. But here it's a center point loading, so the maximum bending moment is at the center. But even though you are seeing the damage spread, in spite of this concentrated load. So that is the special quality of these ductile concretes. They can spread the damage because of material's tensile ductility. Okay. All right, so that's okay. All right, just start.
Forward.
Now this can take clearly much more load, much deeper beam.
You see that bend before it breaks?
Yeah, same thing as that. So now here, of course, due to flexure, we will see vertical cracks, and then at the bottom again, you will see those parallel cracks. So if we do the same test for normal concrete beam, it just has one fracture, and then boom, it's it right away. So now you can see actually the load bouncing around. So what happens is it goes to a point, then it comes down a little bit because a new crack starts. Okay, and then it comes back up, comes back down, so like that. So the machine is still, so this bottom part is still going up relative to the top. So you are still bending the beam. But it's not moving as fast as before, so that elastic stage is over for the beam. It's now going in that inelastic deformation. So where is Chris? Chris, you can actually see the load rate here. The problem that we had with the other class, the lab class. So in this setup, yeah, you can see the load rate here, pounds per second. See, the load is decreasing, it seems. Let me hold it. The status of the beam. This is correct. Okay. Take it out. Okay, so yeah, I want to focus on this part here. So this is the bending of this beam, and you can see these flexural cracks, very tiny microscopic
Can you raise
flexural
it up a little
cracks.
bit?
So
White
you
is
can see
spray.
that here.
Yep.
Okay. So you can see it more closely. Okay, so we started the second test. So you see initially it will run really fast, the load, because it's under elastic condition. But after that it comes down and you see, going very fast. Racing away. After a while this starts, yeah. There must be a threshold set there somewhere. Which is doing that. So we are increasing the load at this rate, 120 pounds per second, 100 pounds. But after a while you will see this load rate to drop down like that. So you remember the last beam also failed somewhere around 6,000 pounds. So it will, we expect the same level.
Is there any difference between this one and this one?
No, exactly the same. So we do multiple tests for each material to get the standard deviation and average. Material behavior. So you see the load rate has dropped down significantly because now it's inelastic. Sometimes it's also 0 or even negative because when the crack forms, the fibers are not very taut at that point. So it takes like a boom to get the cracks, to get the fibers in action in that cracked zone. So this beam has performed much better than the last in terms of load. I think the last beam was not set properly. There was different clearance from both sides. See, now you see the maximum load also drops sometimes. Yeah, see. So now it's going down. So these are the, again, flexural cracks emanating from the loading where we loaded the roller. Okay, so these are all the flexural cracks. Okay, and if I flip the beam this way, you can see the cracks which you saw on the plate, on the bottom belly of the plate, bottom side of the plate. Okay, so these are basically these cracks as seen from the bottom. So these are basically crack planes. Basically this crack throughout the beam, so which you can see on this side as well. Okay. So normal concrete would really fail with just one crack. It has no reason to form multiple cracks. You can see multiple cracks if it has conventional reinforcement, but this beam does not have any steel reinforcement, just the tiny fibers that we added. Okay. So that are the secondary. Two smooth sides, okay, not on the rough side, so that there is no need for any capping. So in just about a moment it is still coming in contact. So the top grip here, it actually has degree of rotation in all the three axes, okay? Because the surface of the cube may not be perfectly parallel to that. So it is free to move in all sorts of directions. So that's what it's doing right now. So the load is still 0. So it's a 2x2 cube. Okay, so it's a very simple calculation. Load divided by 4 will give you the strength in psi. Okay, so this is the pounds per square inch. So in compression, it can take much larger, even a small cube, right? So when it hits 6,000 pounds, it's 1,500 psi. So it can still go much larger. 7 ksi, so about 28,000 pounds. Hopefully. So normal concrete strength is about 5,000 psi, so roughly 20,000 pounds. But this this concrete has greater strength. But more important than strength is the way it will fail. So it won't fail in a catastrophic explosionary way. So if you have ever tested high strength concrete or very high strength concrete, it can actually explode on you. And that's why they have provided all these grills around the machine to contain that failure inside. But there is no danger of that happening with ECC cube because the failure mode will be very ductile. So you will have multiple vertical cracks and you can actually form a pancake. You can keep squeezing it and it will be a very flat pancake. So ductile. It will never disintegrate. So yeah, now it is almost 5,000 psi. Yeah, it is 5,000 psi. 6,000 psi. Now it is 7. So about 50 megapascal. Okay. May actually go higher than that. Okay. Yep, now it is almost at the failure. Yeah. You see the load stabilize and now it will again start coming down. I will let this run for some time. You'll see those cracks. So see, nothing disintegrated. Okay, it already has surpassed its peak. Okay, but still it's standing. So this is very important. I mean, think about an actual column of a building. An earthquake hits and it's not rupturing or your bars are coming out or concrete is exploding around your cover. Nothing like that. It's still standing. Okay. They still give sufficient amount of time for inhabitants to run away. Okay. So although the load is decreasing, but very slowly, very, very slowly. Okay, so we'll stop at that retraction. So, and keep it going, keep it going. Pull this out. Try to look for those vertical cracks which you can see on the camera. Very tiny cracks. So, if you see, zoom over here, there is one little crack over here, one vertical crack. Okay, and I'm trying to find others. Okay, so I flip this cube on the other side and there is some crushing of concrete over here. Okay, again another vertical crack at the edge over here. Okay, and if I further rotate it, there is another crack over here. Okay, so the difference between this and normal concrete is that this would actually the final failure will actually depend on the amount of the bond of fiber and concrete rather than the compressive strength of it, because the tensile failure is actually governing the compression failure here, okay, the pulling out of the fibers. So if the fibers hold on to it, it will take a really long time to pull it out. So what can happen is actually you can keep crushing it, and it will turn into a pancake, very, very flat. Okay? It will never disintegrate. There is no dust or any fractured material around. And if you ask Chris, he will tell you when they test concrete, there are like people have to clean this up for the next half an hour. And nothing like that here.
No cleanup with your stuff.
No cleanup with that. This is clean. All right, so we'll do one more cube test. So the loading rate, I am controlling it because we don't want it to be too fast, because like any other material, the strength of a material, concrete strength also depends on the rate of loading. So if you load it much faster, the apparent strength that you will see will be higher. That may not be the same as the strength under static conditions. So that's why I'm trying to control this load rate under 200 pounds per second. Otherwise it will be too fast. So the standard says, so that's why the ASTM, which one? I forgot. Seed?
37.
No, 39 is for cylinders. There is another one for cubes. So that standard says that the loading rate should be below 50 psi per second. So 50 psi means 200 pounds per second, because the area is 4 square inch. And there is also a difference between the strength that you get from a small cube like this versus the strength that you might get from a 6x12 cylinder. Okay, because we saw in fracture mechanics that the strength is an inverse ratio of the flaw size, right? So as you reduce your specimen size, the size of the flaws also decreases, and that's why the strength in the specimen increases. Okay, so that's just the fracture mechanics size effect in this kind of material. Well, it's true for all concretes and other materials as well. So the strength that you get from this will be about 15% greater than a 6x12 cylinder. Okay, so that again comes from fracture mechanics. So now it's not going high as fast, right? That means it is close to its ultimate point. It is still going up, but not the speed has slowed down. So that curve is in that stable plateau region, and after that it will go down. So this also has cleared 7 psi. How much was the last one? Do you remember?
76.
76. Okay. Well, this doesn't seem like it will get there. We'll see. Yeah, this is going down now. Quite rapidly. Okay. Handle that. Now we can have some fun with that. So now you can actually see multiple vertical cracks over there. Although now there is a very large crack in the middle, so if the fibers don't hold on to it, it might break into two. So might contradict my statement. We'll see how well we can do. So, but I'm also now pushing it much harder. I'm just going it from like that. See, now you can see some dust also coming from it. So you can already see that the specimen has gone beyond. So that diameter of that bottom one is 2 inch exactly. So it should be within that, but now it's going outside of that. Still holding on. So this is significant compression. I mean, in reality, you would never see this kind of compression. It's like more than 10% already, I think.
It's good. It's good to do a test like this.
Yeah, exactly.
It's a good idea.
Yeah.
Whose idea was that?
Jerry's, I think. Jerry, you encouraged us to make the pancake out of it.
Which load is it carrying right now?
8,000 pounds. So the fibers really hang on to that. I mean, don't let go. Very funny looking specimen now, but it's still carrying load. Now you can really see that squished form of the specimen. Huh? Anybody got some syrup? So yeah, that part that you're seeing is really not doing anything. It's just hanging on to that. The core is still what is taking the load. Okay, should we pull it out? Okay, there you go. That's your pancake. So the core is still there. Okay, although these peripheries have been removed, the core is still there. Okay, it's almost very small, almost 1 inch. Okay, 50% deformation. All right. Okay, so that's your ECC.